Hi, welcome to the demo session on lists and built-in functions on lists, etc. So let's you see the terminal here. Let me inside Visual Studio Code. Let me start GHCI. So we've been looking at list functions. So just to recall, you can always build lists by starting with empty list and prepending one element after the other, but you prepend the element. You start with the empty list, prepend 3, prepend 2 and prepend 1, and you'll get the list 1, 2, 3. Right? This is the kind of thing that we have been seeing. We also saw in the last week itself some basic functions with pattern matching on lists. For instance, we saw that you could do myLength of empty list equals 0, myLength of actually you don't even need the x, so you can actually say underscore colon xs is 1 plus right. We saw this. Yeah, one thing you will notice is that for this myLength I have not given the type. So let's see what will happen if I load this. Surprisingly it works. It's not a surprise actually. Haskell doesn't expect you always to give a type, but we will follow the discipline of providing all the types because we are learning Haskell now. But as we will see in 4-5 lectures, Haskell doesn't expect you to give a type. It will figure out the type on itself, and even if you give a type, what it will do is it will check whether the type that you have provided is compatible with the type that it has figured out for this. Yeah, so we'll look at this nice feature later. It's called type inference, but for now we will provide types everywhere. So this is myLength list a arrow int. Then if I save this, and if I go back to GHCI and reload it by doing :r, okay, so now I can ask for myLength of 1 ... 10. Now that we know the dot notation, yes, it gives the value 10. Okay, and we also did various other things, right? We did things like add an element at the end, and we called it add at end, or I actually used some notation for it, hash, let us say, and I can actually define functions. I can actually define operators directly, but I should define the function version of them, which means that when I specify the type, I should put it within parentheses. But after that, when I define it, I can define it like an operator. So hash here is of type list a arrow list a. All I am doing it is to add an element at the end of a list. So I will say empty list hash x is the singleton list x, y : y is slash x, hash x is y followed by y is hash x. Okay, and typically one aligns the equals symbol in all the definitions, so one would introduce some tabs. Okay, and that's a definition, and one can check whether this works. 1 ... 10. I should reload once again. 1 ... 10 hash 15, let's say. Yeah, gives you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 followed by 15. Okay, so these are basic functions that we saw. We also saw functions like bang bang an implementation of bang bang, you can check whether if I say 1.5 and I say bang bang 6, I'll get an error, right? Index too large is what I'm getting. And if I say -3, I'll get an error saying negative index. Okay. Okay, good. So let's actually program this thing where we said instead of giving a negative, instead of letting Haskell abort, we can actually do it as an either type. So I can say value at position, or I can actually define it as my own operator. I'll use 3 bangs, bang, bang, bang. Okay, is of type list A int arrow, list A arrow int arrow maybe A, right? No, either string. Right, the string part will tell you that it's an error message, and let's try to recall what all cases we had. So anything bang 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 n, if n is less than or equal, if n is less than 0, then we'll say left negative index. And empty list bang 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 anything, we'll say is left index too large. And then otherwise we have the case where x colon x is bang bang bang, and so it is good to also align all these different operators. So we'll do it this way in the definition itself. And here is just one small thing. If it's just a single guarded definition, you could make it just part of the line itself like that. So you're saying that in case n is less than 0, then you just give negative index as the error message. So now it's all aligned. So it's easier to read the code and figure out the different cases. X colon xx is at 0 is just x, but I can't just say just x, I should say right x. Okay, so that's a definition. So let's see how it works. I'll go to GHCI. I will reload the file. It compiles, thankfully, and I can ask 24 dot dot 100 bang 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 33, let's say. Yeah, it gives right 68 because 2, 4, 6, 8 and so on, it will go. Let's see what is the largest index possible in this. If I ask for 0, it will say write 2. If I ask for 49, it will give me write 100. So if I say 50, it should say index too large. But note that it is giving some value, it is giving an error message, but it's putting it inside a left. So it is up to you how to handle it. It won't produce a runtime error, unlike the version which calls the error function. I could also say 2, 4, this thing -3, -1 even, doesn't matter. It will say negative index. And since this bang bang is an inbuilt, is an infix operator, I can just give -1 without, oh no, I will get an error. Okay, so I should give -1 within parenthesis, then I get this. Okay, so that's a version where I use the either type. Let's get back to the file. What else can you do? So you had this hash. Using the hash, we had a version of plus plus. Let's try the built-in version of plus plus, which concatenates two arrays, two lists. One dot dot 50. Let's do this. 1, 3 dot dot 99. All the even numbers first and then all the odd numbers. 0, 2 dot dot 98 plus plus 1, 3 dot dot 99. So I'll get 0, 2, 4, 6, 8 all the way till 98 here, and then I'll get 1, 3, 5 etc. all the way till 99. Right. So that's the plus plus operator, which, if you recall, does recursion on the first list. Okay. So that's plus plus. We've seen plus plus. We saw our own version of bang bang bang, which is to report what the element is at the a particular index. Okay, fine. So then we introduced take, drop, etc. We'll come to that in a minute. In the last week itself, we defined this my reverse, which was the naive my reverse, which is to just say reverse of empty list is empty list, reverse of x followed by x's is just that you reverse x's and you put x at the very end. And rather than saying plus plus this singleton list x, I could also have used my hash function. So and that's my reverse, and I could just reload the file and just say my reverse of let's try 99, 98 dot dot 0, and reverse of this should be 0 to 99, right? So notice how if I just say 99, 98 dot dot 0, I'll get the whole list in reverse. But if I do 90, if I forget the 98, I'll get the empty list. Okay, so this is something that you need to remember when you use descending lists. Okay. Here is a nice feature in Haskell, which is that you can actually compute programs in some sense, right? Because look at what this is not Haskell that will compile, but I have put something in the comments here, and it's nice to figure out what is happening. Let me remove the comment so that it's highlighted better, the code. Okay, so I am defining reverse into as this thing. Reverse L into the accumulator means my reverse L plus plus accumulator, right? So the reverse of L should appear before the accumulator. Now this is a version of reverse into, this is a more complex function, and I have defined it in terms of my reverse. But now there is a way to directly define this function rev into without referring to my reverse, and that you can derive just by expanding these equations, right? See, reverse into accumulator of empty list is nothing but, just expand the definition, my reverse of empty list plus plus accumulator, but my reverse of empty list is empty list as given by here, right, as given by this line, my reverse of empty list is just empty list. So instead of my reverse of empty list here, you can just use empty list. But empty list plus plus accumulator is just accumulator. Okay. So now you have one line in the definition of reverse into, and this is a direct definition without referring to my reverse. Okay, because we are doing this whole exercise so that we can improve the performance of my reverse. Okay. What about reverse into an accumulator of x colon xs? Let us figure it out. It is just expanding the definition of reverse into, it is my reverse of x colon xs plus plus the accumulator. But my reverse of x colon xs is nothing but my reverse of xs hash x, let me say now. Yeah, but that is nothing but, in fact, I should actually write it plus plus singleton x for my equations to work. Okay, but plus plus is actually associative. So if I have to add L1 plus plus L2 plus plus L3, I can do the plus plus in either order. So here my reverse of x's plus plus singleton x, and then this whole thing plus plus accumulator. I can rewrite this by putting the parenthesis here. I do singleton list x plus plus accumulator, and then I do my reverse x's plus plus that. But singleton list x plus plus accumulator is nothing but x followed by accumulator. So that is this. So but this my reverse of x's plus plus x colon accumulator, this is back to this pattern. You see the right hand side pattern of the definition of rev into. So this is nothing but rev into of x colon ac of x's, right? So that's it. So now I have, if I look at this chain of equation, I have rev into x colon x's equals rev into x colon accumulator of x's. And here I have rev into accumulator empty list is just accumulator, right? So I have this equational way of deriving a new definition, and I just put that as the new definition here. So now I will comment out all this because that was just some explanation to tell you how to arrive at this. This is not an exercise that you need to remember completely now, but this is just to tell you that this is a nice cool thing that you can do in Haskell, which is that you can sort of like computing some algebraic equations, you can just expand definitions and equationally reason and then arrive at a new program. And this new program is actually a more efficient version of my reverse, because you can finally do fast reverse is nothing but reverse into the accumulator, reverse into the empty list as the accumulator. Okay, and yeah, so that's about reverse, etc. We introduced more functions in the lecture. Let's look at some of them. Let me reload this and let's do fast rev. In the last demo session, we actually demonstrated reverse of fast rev on even some large lists, right? 0 dot dot 100,000. And it starts printing immediately, right? Which is a good thing. It will of course take some time to print out 100,000 numbers, but it's quite quick actually. There are ways in GHCI where you can add some options so that after every command you will get a report of how much time, how much space was consumed, etc. I would advise you to refer to the GHCI manual for all that. Okay, so this was about reverse, etc. We looked at take and drop and so on. Just to tell you, take of -3 of 0 to 9 should actually give the empty list, right? So we'll take of -1. So we'll take of 0. Right, and similarly drop 0 of 0 dot dot 9 is 0, 1, 2, 3, 4 till 9 because you are not dropping any element at all, right? And if I say take 1000 of it won't give an error saying index too large or anything, it will just take however elements are available till you exhaust the list or you go beyond 1000. That's it. So it returns this, and drop of this thing will actually try to drop 1000 elements, but once you reach the empty list, it will just return empty, and it won't return any errors or any such. Okay, good. But if I say drop 1000 of 0.1000, remember 0.1000 has actually 1001 elements, and if you drop 1000 elements, you will get the singleton list containing the value 1000. Okay, so this will work. Okay, this is take drop, and split_at we saw, and that I have written here as a function take drop, because split_at is a built-in function, so I have written it as the function take drop. Take drop of any value on empty list is empty list. Take drop n x colon x's is if n is less than or equal to 0, then you return empty list and x colon x's, else you use this format, let y z is equal take drop n minus 1 x's in x colon y z. Okay. Okay. Yeah. So now you had these functions which we had, divisors, etc. Let's just look at divisors of 120. Let's see what we get. You get 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, 30, 40, 60, 20, 120. So yeah, so these are all the divisors. I can ask if 120 is a prime, right? There is no function called prime that I have defined, but I can define a function is prime, and I can define it right here even. I can just say, or I can directly write it as an expression. I can ask, okay, is prime x equals that's it. Okay, and now I can ask is prime of 120, I should get false. Is prime of 21 should get false. Is prime of 23 should give me true, and so on and so forth. Okay. In fact, let me go back and install this definition in the file. So now I can say, yeah, I have a definition, is prime, and then all primes less than or equal to x is p from p drawn from 1 to x, and then you check whether p is a prime or not. Only then you output it. So let me reload, and I can ask all primes less than or equal to 1000, let's say, right? So this is the list of all primes that are less than or equal to 1000, 2, 3, 5, 7, 11, 13, 17, and so on. We will see a much cooler way of generating all primes later, but for now this is a quick way of checking, generating all primes till some reasonable number, till even 10,000 it should work fine without much of a, yeah, it takes some time, but still, I mean, this is much more than what you would expect in other programming languages. Of course, you can do a much faster job of generating the primes, but to write the program, you can see that writing this program here in Haskell was extremely trivial, right? All I had to do was just do this using list notation, just do this is prime, which is a trivial definition, and then generate all primes. Okay. And yeah, so in this file I also have all these other functions like capitalize, position, etc., etc. Let's actually try to right. So here is a thing with this upper. So there was in the definition of 2upper, we just used this offset, right? We used the offset there, but the offset is defined here. So the point about a local definition using where is that if I have a guarded definition with multiple guards, the where clause applies to all the guards, not only to the, it looks as though as this where clause applies only to the second guarded definition, but no, the local definitions defined using the var class applies for the whole definition as such, okay, and this whole including both these guards are part of one definition, okay. Yeah, whereas I couldn't use, if I had to use let, I could have used let, but for instance, yeah, so here I can use let, but this offset is defined only for the first class here, because this let definition is part of the right hand side expression, whereas the var class is part of the whole definition, okay. These four lines form a whole unit, including the var, whereas as a let definition, this let offset equal to this thing in offset, that's a standalone expression, you can put it anywhere you want, okay. So this let can occur as part of any definition as a local definition, as part of any expression as a local definition, whereas var can only occur in some specific places where you are actually defining like this, okay. It cannot be part of an expression, it has to be part of a definition, okay. This is the important thing to remember. Var is part of a definition, let is part of an expression, okay. So these are two styles of defining the same two upper function, okay. Fine. So let's try to use this position thing. Let's upgrade this position to a maybe, okay. So then we are saying that position is char arrow string arrow maybe int. Position C empty list is just 0. Sorry, position C empty string is nothing. Position C d colon d is if C is equal to d, then just 0, else 1 plus, else it is just of else I have to do a case position CD is off, nothing means nothing, just P means just P plus 1. Right. Now, there is a problem, because if you use this position, then you have to again do a case construct to actually deconstruct what the value is, if it's nothing or if it's just P. But maybe that's a price you are willing to pay for streamlining this code, because you don't want to return actual integers when you want to return a null value, okay. So that is the real point about using maybe, it is to structure your code better. So let's check what happens here. Okay, I can say position K right, I'll get just 3, but I can ask position D in Haskell is cool and I'll get nothing, okay. So this is the kind of thing that you can do. And then there was this word count program which you saw, we can actually check how it works. This was exactly the same thing that was given in the slides. You try to count the number of transitions from space character to non-space character, and you start the whole process by adding a space by fiat to the front of the list, okay. And here you say go of singleton character means there is no space to non-space shift. So you will say the number of such shifts is 0. If it's C colon D colon D is, then you will check if C is a space and D is not space, in which case you will add 1 to go of D colon D's, otherwise you will just say go of D colon D's, okay. Okay. And actually, just to tell you that this kind of if statement is also an expression. It's not a statement, but it's an expression. I could actually do something like this. I could actually say go of d colon d is plus, and I can give an if expression as part of a larger arithmetic expression also. But in this case, what I'll do is I'll do this. Right? If C is a space and D is not a space, I'll add 1, otherwise I'll add 0 to go of D colon D's. This is actually a much simpler way of writing the same thing as earlier, because it's very clear what you are doing, right? You have to make a recursive call to with argument D colon D's, and then you decide whether to add 1 to it or not based on whether this condition is fulfilled or not. Okay, so that's sometimes a cleaner way to write a program. So this is just to tell you that if you can have, as part of larger expressions, you can have if expressions, okay, not only at the outermost level. Okay, so let's see if this compiles and works well. Let me reload. Yes, and word count of so let's put lots of spaces in between. Okay, and you will still get 9 words because Haskell is cool. There is not a cooler language. Okay, even though there are lots of spaces in between. Okay, so this works. Okay, good. So this is just some sampler of some of the things you can do with lists. We'll in the next week's set of lectures, we will resume our discussion of lists. We'll look at more advanced functions. We'll look at this thing that I mentioned called map. Okay, and then we'll learn more about lists and do more interesting programs. Okay, thank you very much. I will stop this lecture now.